All right, our next lesson in chapter 3, we are going to be doing 3.4 today. We're going beyond CPCTC. So we've learned how to prove triangles are congruent. We learned after that we have proven triangles congruent how we can show that all the corresponding parts of those two triangles are congruent. So we can get a lot of great information from congruent triangles. And today we're going to talk about beyond CPCTC, some other interesting segments and things that we can do in triangles that are called medians and altitudes. And then just making sure we remember all about those auxiliary extra lines and things like that. So we're going to talk medians and altitudes in 3.4 today. So before we get into that, just a little bit of a warm up here, a little algebra to bring it back. Here we have triangle ABC is congruent to triangle ADC. And then you have 4 different angle measures given. You just need to solve for X and Y. Go ahead and pause your video and take a shot at it. Okay, so the first thing that I would do is I would say, okay, triangle ABC congruent to triangle ADC. And then whenever I see triangles congruent or when I prove triangles congruent, I like to highlight them in different colors. Just so I know, like, hey, I've already proven these guys congruent. It's kind of my indicator. All right, so those two triangles I already know are congruent. Then it says angle 1 is x plus 8, so I'm going to put that in my picture. Angle 2 is 2x minus 5. Angle 3 is 3y minus 7. And angle 4 is 2y plus 8. So I've put all these in my picture. Now, since I know that my triangles are congruent, I can use CPCTC to say that I have some congruent angles here, right? Since everything that I was given was an angle measure, that means that I should have angle BAC is congruent to angle DAC, right? Or kind of if we're just using our single letter there, angle A is congruent to angle A, right? So I can set up one equation saying x plus 8 equals 2x minus 5. Now I notice in that equation there are only x's, so I should be able to solve that right now if I wanted to. But I know that I'm going to need a second equation because I do have a y in my picture. But I also believe that angle B is congruent to angle D by my corresponding parts, right? So angle 3 is congruent to angle 4. So I could set up my second equation, 3y minus 7 equals 2y plus 8. And now I have, but in that equation I notice there's only y. So I have my two equations. I could have solved one at a time either way. Hopefully you got that figured out. But let's go ahead and do that. So let's see, I would subtract x from both sides on this one. I get 8 equals x minus 5. And then I would add 5 to both sides. So I get x equals 13. Okay. On this other side then, let's see, I would subtract 2y from both sides. I get y minus 7 equals 8. And then I would add 7, and I get y equals 15. So x equals 13, y equals 15. Hopefully those weren't too difficult of equations to solve, but I know the more that we can bring back that algebra, the better. All right, so that was a good little review of using that CPCTC to find other things, right? So what we're going to talk about today are two new things. The first one is called a median, and the second one is called an altitude. So we're going to start with a median. So here is the definition of a median. If a segment is a median, then it is drawn from the vertex of a triangle and splits the opposite side into two congruent parts. Ooh. Just tried to get too close to the edge. 2 congruent parts. Okay. So you can kind of think of like a median in the street, right? A median in the street goes right down the middle of the street. Well, a median in a triangle does the same thing. So if I was going to draw a median from L, it has to be drawn from the vertex of a triangle. And it is going to go right smack dab to the middle of the opposite side. So it's going to split the opposite side into 2 congruent parts, right? Now, that's the most common way to see it, where it splits the opposite side into 2 congruent parts. However, when we see that this point splits the opposite side into 2 congruent parts, we could also say that that point is the midpoint, right? So we could swap words out here and say if a segment is a median, then it is drawn from the vertex of a triangle to the midpoint of the opposite side. So we could swap out that highlighted part, splits the opposite side into 2 congruent parts, to the midpoint of the opposite side because it means the same thing. But I'll tell you that the one that we use the more often in proofs is that it splits the opposite side into 2 congruent parts. All right, now this is a definition, so we know it's reversible, but I am going to write down the converse right now, and I highly recommend you do the same thing because the converse is used just as often as this version is. So we're going to switch the if and the then. So if a segment is drawn from the vertex of a triangle and splits the opposite side into 2 congruent parts, then it is a median. All right, so there's the converse. And again, you can swap out the words splits the opposite side into 2 congruent parts with to the midpoint of the opposite side, and that works as well for both. So just keep in mind that this highlighted part you can swap out in either one, and that is perfectly fine. So this does seem like quite a long if-then form, and it is, but every single part is crucial. For it to be a median, it has to be drawn from a vertex, okay? And the only medians of triangles, that's it. So it has to be drawn from the vertex of a triangle, and it has to split that opposite side into 2 congruent parts. So it's just a lot of words, but they're all very essential. Now, I drew in the median from L, but I could have drawn in a median from point M, right? M is a vertex. So I could draw it over here as long as I'm splitting the opposite side into 2 congruent parts. That's a median. I could also draw it from K. And I would go to this midpoint of this side, and then that's a median, right? So there are 3 medians in every triangle, no matter what. 3 medians in every triangle, and these medians will always be inside the triangle. When I have to go to the midpoint of the opposite side, that segment has to slice right down the middle of that triangle, always inside the triangle. All right. So you've got 2 new if-then forms there, and you have 2 little pointers about medians, is that there's always 3 in every triangle and that they're always inside the triangle. All right, so a little practice for you. Can you just practice drawing in the medians? So for each of these 3 triangles on the top, not the one down at the bottom, but each of these 3 triangles at the top, can you draw in the median to side QS? So from the vertex across from QS to the midpoint of QS. Go ahead and see if you can do that. Pause your video. All right, so if I look at my first triangle, I would have to be starting from R, going to the midpoint of QS, and I'm going to mark my picture to indicate that that is the midpoint. All right, the second one here, the middle guy, starting from R again to the midpoint of QS, indicating that that is the very center. And then the last one, starting from T, going to the midpoint of QS would be something like this. All right, so hopefully you drew the same types of segments. Again, you're going to the midpoint of that opposite side, from the vertex to the midpoint of the opposite side. Now the one on the bottom says, is the segment VW a median? Why or why not? Now right now, I don't even know if V or W are midpoints, right? So that would definitely be a definite why not. But let's say that I even tell you that V is the midpoint and W is a midpoint. Is it a median? And the answer is no. Even if they're both midpoints, it's not a median because it's not drawn from the vertex. For it to be a median, it has to be drawn from a vertex of that triangle, okay? V and W are not vertices, so of the triangle, so they are not, that's not a median. So that's why it's really essential that we include all of those words in the if-then form for median. All right, so median, it goes to the midpoint of the opposite side. Altitude now is the second one that we have. So median, you think of the middle of a road, right, with the grass and the trees going down the middle. Altitude, you think height, right? And whenever you think about height, you think straight up and down, forming right angles. So the definition of an altitude, so definition, I'll leave a little more space here on this one. If a segment is an altitude, then it is drawn from the vertex of a triangle again and forms right angles with the opposite side. Altitude means it's forming right angles. Now, it doesn't have to go to the middle of that opposite side this time. It just has to be straight up and down with the opposite side, forming a right angle. So if I draw in my altitude from L, it's going to go straight down from L and form right angles with that opposite side. So notice it is not going to the center of MK, it is coming straight down from L, and it's forming right angles with MK. Now, another way to say forms right angles with would be to say is perpendicular to, right? And is perpendicular to the opposite side. That can be swapped out here. But we more often see the words right angles than we do perpendicular. So the way that I wrote it originally is the most common way that you will use it in a proof. But perpendicular is another way to say the same thing. So you could swap that out. All right, again, this was a definition, so we can write our converse. I am going to write it down. I highly recommend you do as well, because the converse, again, is used just as often as the original on this. So the converse would say, if a segment is drawn from the vertex of a triangle and forms right angles with the opposite side, then it is an altitude. All right. And again, forms right angles with can be swapped out for is perpendicular to if needed. All right, again, it seems like a lot of words, right? But the words are almost the same as median, so that hopefully will help you remember them a little bit better. But every one of those words is essential. It has to come from a vertex to be an altitude, and it has to form right angles with the opposite side. Okay, now just like and median, in this one, I drew the altitude from L, but I could also draw the altitude from M. It's a little bit trickier, but it would probably go something like this. That seems to be where it would be forming right angles. And I could also draw one from K. All right. Forming right angles from K would probably be somewhere around here. I hope that yours is a little bit straighter than mine. Pretend that goes straight into the vertex there. So there are always 3 altitudes in every triangle. But on this one, since I have to form a right angle with the opposite side, we do have some interesting situations. So I'm going to actually move down to the next problems here where we're going to practice drawing in altitudes. So on these two, it just says to draw an altitude from point A. So draw the altitude from vertex A in each triangle. Why don't you go ahead and take a shot at it? All right, the first one here, if I'm drawing from A, it has to be perpendicular to BC. So it's going to go something like this, right? Now note it's not leaning over here. There's no way these are right angles. So make sure that your segment actually looks like it's straight up and down with that opposite side. Now, the second one is the tricky one. It has to come from point A. The opposite side from point A is BC. I have to go from A and be perpendicular to BC. Well, the only way for that to happen is for this segment to be landing way out here, right? This is where there's going to make a right angle. That's the only way to make a right angle with that segment BC. Now you might argue, but it's not even hitting segment BC. But remember that any segment can become a line, and the only way to make a segment that's going to go straight down from A and land on that line BC is for that to be outside of the triangle, and this is okay. All right, so altitudes can be outside the triangle. That's a little bit of a tricky thing to wrap your brain around. So just keep that in mind. All right, and I'm going to actually take this and we're going to copy it and we're going to put it back up on this first slide here too. So just so that you have it in more than one place. Altitudes can be outside the triangle. And there are 3 altitudes. But when we looked at our median, medians are always inside because they have to go to the midpoint. It's got to slice through the middle. And altitude has to form a right angle, so it doesn't have to be inside the triangle. It can be outside the triangle. It even could be a side of the triangle. If you had a right triangle, so if you have a triangle that looks like this, I apologize, say you know that this is a right angle, then we would say that segment AB is the altitude from A. So an altitude can be outside the triangle, an altitude can be a side of the triangle, or the altitude can be inside the triangle. So you have lots of options for altitudes. Okay. All right, so let's practice using these in a proof then. So here's our picture, very similar to our warm-up, but now we're given a little bit more. So this time we're given segment AB is congruent to segment AD, and angle 1 is congruent to angle 2. And we're going to prove that AC is the median to BD. All right, so first step is to get our givens written down and marked in our picture. AB congruent to AD. And step 2, angle 1 is congruent to angle 2. And that's up here. All right. Now, my goal is to prove that AC is the median. And remember that to prove that it's a median, I would have to prove that it's coming from a vertex, which I can see in my picture, and it's splitting the opposite side into two congruent parts, right? So I have to prove that segment BC is congruent to segment CD. So hopefully after the last few days with our congruent triangles idea, you're kind of seeing that maybe I could use the reflexive property here. Step 3, AC is congruent to AC with the reflexive property. And then once I have that, then I can see that triangle ABC, is congruent to triangle ADC. ABC congruent to triangle ADC. And my reason would be side, angle, side. And the steps should be pretty obvious, but that first step was a side, the second one was an angle, and the third one was my other side. So 1, 2, 3. All right, so now that I have my triangles congruent, again, I see that segment BC and segment CD are my corresponding parts of those congruent triangles, right? BC and DC, so step 5, segment BC is congruent to segment DC. And the reason is corresponding parts of congruent triangles are congruent. Okay, and just remember your self-check there. In order to use corresponding parts of congruent triangles are congruent, CPCTC, I need to make sure that I have said that I have congruent triangles. And I do have that as my step before that, so I'm okay to use CPCTC here. Okay, so I just proved that those two segments were congruent. So AC is coming from a vertex, and it is splitting the opposite side into two congruent parts. So I am ready to write my proof statement. Step 6, AC is the median to BD. And now I have to make sure I get my if-then form in the correct order, right? The step before this, I said that I had two congruent parts. So the two congruent parts is my if. And what I'm saying in this step is that it is, is that it is a median. So the if part needs to be the two congruent parts. The then part needs to be the median. So if a segment is drawn from the vertex of a triangle and splits the opposite side into two congruent parts, then it is a median. Okay, so again, the then part needs to be the median. The if part needs to be this two congruent parts, right? Splits the opposite side into two congruent parts. And you have to use all those other words, right? It has to say it's drawn from the vertex of a triangle because otherwise it wouldn't be a median. All right, so there is good practice. Now that was using the one version, kind of the converse for the median, right? That's if you're trying to prove something is a median. So this next proof, this time I'm given that I have an altitude, and I'm going to try and use that to prove something else. So I'll kind of show you how that goes. So in this next one, we are given that CD is an altitude to AB. Move this over just a little bit. There we go. All right. CD is the altitude to AB. Now, before I can really move on past this one, I really want to wrap my brain around what that means, right? CD is the altitude to AB. It means that I have right angles right here. So I could say angle CDA and angle CDB are right angles right now, just knowing that I have an altitude. So I'm going to include that in my statement because I'm sure that that's going to come into play. So I'd say angle CDA and angle CDB are right angles. And now the reason is the definition of an altitude, but I have to make sure I get my if-then form right again. So remember, the if is what comes before. So what came before is that it was an altitude. That's the if part. The then is what I'm saying in this step, and that's that they are right angles. So to get my if-then form right, I have to say if a segment is an altitude, then it is drawn from the vertex of a triangle and forms right angles with the opposite side. Sorry, trying to save some space and I keep hitting this, sorry. Okay. All right, so there's a good if-then form for that. Okay, now what else am I given? Step 3, segment BE is an altitude to AC, given. Okay, so if BE is the altitude to AC, that means I have right angles right over here, right? Angle BEC and angle BEA. So I'm going to include that as step 4. Angle BEC and angle BEA are right angles. And that reason is exactly the same as step 2. And goodness sakes, I do not want to have to write all that over again. So I'm just going to say same as 2. Our good if-then form for altitude. So again, the then part was the forming right angles. The if part was that it is an altitude. And the same thing is happening here, right? I knew that it was an altitude, and I am proving, I'm saying in this step that I are right angles. So it is the same if-then form. All right, now step 5. Our last given is that segment AD is congruent to segment AE. And that was given. AD is congruent to AE. And I'm going to try and prove that segment DB is congruent to segment EC. Okay, so I'm trying to prove, whoops, here, DB is congruent to EC. Okay, how am I going to do that? Let's see. Well, what I see here, and this is a little bit tricky, so I'm wondering if you'll be able to see the same thing. What I see is, I'm going to grab a different color highlighter, and I see that I have this segment So I have this segment is the side of this green triangle. I have this right angle here, and I have angle A in the green triangle. And then if I over here and I look at this blue triangle, I have a right angle here, I have this segment, and I have angle A. I notice that angle A is overlapping there, right? So I could say, step 6, angle A is congruent to angle A by the reflexive property. Okay, and I do have two right angles there, angle ADC and angle AEB, and I've already said they're right angles, but I still need to say that they are congruent, right? So step 7, angle ADC is congruent to angle AEB, and the reason is if two angles are right angles, then they are congruent. Okay. And now I have that those two triangles that I highlighted are congruent by angle, side, angle, right? Angle, AD and AE were my sides. These right angles were my other angle. So step 8, triangle ADC is congruent to triangle AEB by angle, side, angle. 5, 6, and 7. Ooh, we got a lot going on. Okay, now if I have those two triangles are congruent, then these big long sides will be congruent, right? See, that big long side AB would be corresponding to the big long side AC. AB and AC are corresponding, right? So step 9, segment AB, whoops, is congruent to segment AC. Corresponding parts of congruent triangles are congruent. But I'm just trying to get the bottom parts. I already knew the top parts are congruent. I now know that the whole big parts are congruent. So the bottom parts would be congruent by the subtraction property. Step 10, DB is congruent to EC. Because if two congruent segments are subtracted from two congruent segments, then the differences are congruent. I'm running out of space. Squeeze it in. Whoo, that was a proof. So that was a pretty long one, but you can see now that we're getting all this information from our congruent triangles and our CPCTC and now our altitudes and medians, we can go so much farther. We can prove so many things in these pictures using all of that information as long as we build on it. That was a pretty crazy one to throw at you right here, but that's why I thought we would do it together. So just, I really want you to know, notice, see the difference. So on that first one that we did, how to prove something is a median and get that if-then form in the right order. And then in the second one, the really big thing I want you to take away from it is how to, if we're given that we have an altitude or median, how to get that if-then in the right order and use that information to go farther. So that's the big idea for the lesson today. Remember, a median is drawn from the vertex of a triangle and splits the opposite side into two congruent parts. An altitude is drawn from the vertex of a triangle and forms right angles with the opposite side. There are 3 medians and 3 altitudes in every triangle. Medians have to be inside the triangle. Altitudes can be outside the triangle or also can be an actual side of the triangle.